Okay, so today we'll be looking at one of the questions from the Australian Maths competition. So the question says, the interior of a drinking glass is a cylinder of diameter 8 centimeters and height 12 centimeters. The glass is held at an angle of 45 degrees from the vertical and filled until the base is just covered. How much water in millimeters is in the glass? Okay, so to approach this question, the way I would go about it is I would first draw a diagram of what they're talking about. So obviously the cylinder. First we draw the cylinder just by itself. So it would look something like this. Doesn't have to be to scale, just a nice diagram so we can visualize what's going on. And obviously they gave us the diameter, which is this, is 8 centimeters. And the height of this is 12 centimeters. Cool. So the question's saying, if we tilt this cylinder at an angle of 45 degrees to the vertical, we should get a different area, different volume, essentially, that covers the base. Okay, so the best way to see this is, if anything, to draw like a wall, I guess. So pretend like this is a wall. Let's call this the wall. And let's take our little cylinder and paste it. But then, as you can see, we're going to incline this such that it's 45 degrees to the vertical. So yeah, that looks like it's 45. Cool. So it doesn't have to be too perfect, just as long as we know it's 45 degrees to the vertical. So that's like the base. And say we look at it at the diameter, that's the 45 degrees in there. Cool. So now it may be a little tricky to see the height, because now the height is definitely changed because we're now some units this way. So that's not really important for this question, but what we're trying to find, pretend like this is the water. So if I draw this like this, so there's some portion of this shape that if we keep filling in water from here, that this will fill up with water as we pour more water in until there's like a level amount of water in the cylinder. Cool. So our goal is to find this volume. This is what we're trying to find. Cool. So how are we going to go about this? The best way that I would be thinking, let's just clean this up a little bit. Okay, let's just move this a little bit in. Let's put that there. Let's just make this a little bit smaller. Then let's move this one inwards. Cool. So I would essentially draw this shape that is the water, I guess. So say I draw this water shape. So obviously this is a level part. So we don't know exactly how long this is because obviously we've moved it in such a way that this is now, this diagonal piece over here is some length. So let's just call that length x centimeters. And we have essentially this diameter piece, which is part of this, which forms a triangle. So let's draw that in. So say that this is this, and we can draw this. Cool. And this is that last piece. Sweet. So if I draw this basin as well, that would help. So we can see what's going on in terms of the angles. Okay. So the main concepts of this question would be using your knowledge of triangles and angles to essentially evaluate these lengths and calculate this volume at the end. So let's label this 8 centimeters because this is our diameter. This, we don't know this length, obviously, because it's also changed. So we'll just leave that for now. And we know that this here is angled at 45 centimeters. 45 degrees to the vertical. And that helps us in the way that we know that this also would be 45 degrees, since these are these are alternate angles on parallel lines. So using a bit of geometry now, we can see that these are parallel. This is the base, this is the water level, and these are parallel. So we can definitely say that that's 45 degrees up here. And similarly, if you notice that 45 degrees inclined, if this is 45 degrees inclined, pretend like we're like twisting this such that it moves from like our original position over here to here. That means that this side would also be rotated such that it's 45 degrees from this level. So this would also be 45 degree inclined. So we would have to label this as well as being 45 degrees, and which helps us in identifying that this is obviously a right angle triangle, since this is an angle, straight angle, and obviously 45 plus 45 is 90, and the remainder is 90. So there'll be a 90 degree angle here. And that is very useful now. So since we know this is a right angle triangle, we can apply our usual methods of either Pythagoras' theorem. So now we have a lot more options to use. So when it's a right angle triangle, we can apply Pythagoras, or we can apply our usual trig functions to this and essentially evaluate that method and by that method. What I'm thinking, so to figure out, so what I'm trying to do here is find this area of this shape, right? If I find the area of this shape, I can relate it to the area of the total shape. So obviously there's a rectangle, this rectangle here. So if we look at it in the way that this is a rectangle, the normal, like for example, I'll call this the normal view of the shape. So this is some rectangle with 8 by 12 sides. So obviously the area we can calculate pretty easily is equal to 96 centimeters squared. And let me just call this the normal view. And let's call this the rotated view. So what I'm trying to do here is essentially calculate the ratio of the area taken up by this, essentially the water filling up this portion of the cylinder in relation to the total area. So by that we can calculate a ratio of proportion of area to essentially do the same with volume. So once we calculate the total volume of this cylinder, we can use that same ratio because we know that the areas are in proportion to volumes. Cool. So let me just write that out. So obviously, my goal here is to figure out the proportion of area, proportion in area, which is equal to the area of the shaded blue. So obviously the rotated part, this part, like essentially the area of this triangle, over the total area of the rectangle. So that area is that 96 centimeters squared that we calculated earlier. Cool. And once we do that, we'll essentially get a ratio of the area to the total area, which we can apply to the volume as well. Cool. Okay. So now looking here, we can see that we can actually apply some of our trig functions to evaluate x, because now it's a right angle triangle. We can kind of use that to find x, because that's obviously the base of this triangle, and we know that the area of this triangle is equal to half times the base times the height. And when we're referring to height here, we're referring to perpendicular height. So perpendicular height in this triangle, it's not really obvious, but let's draw that in. So that's the perpendicular height in this case. So it's the one that is right angled to this base. Cool. So evaluating x now. So our base length, we can see that it's x is okay. So going back to our trig functions, we can see that it's actually, so if we write out Towa. So we obviously have an angle here, and we want to relate this, and we want to relate this. So we can see that that's actually related by so obviously this is the opposite, this is the adjacent, this is the hypotenuse in this case. Oh, not this. It'll be, this is the opposite, this is the adjacent. So we're looking at the big triangle. So let me just maybe rub this out for now, because it's probably going to be confusing. Cool. And now we can see that that's actually related by cos, because cos tells us the adjacent with the hypotenuse. So let's label that real quick. So we have that cos theta is equal to the adjacent over the hypotenuse. Cool. And we see that that's related by, so our adjacent side is 8, and we have x, which is related to the hypotenuse. So solving for x, we have 8 over cos 45. Cool, so that's our angle here. Sweet. And now we can move on, and now we can draw that height in again. So we'll be needing this height. Let's label that y centimeters. So now we can see that that's also another right angle triangle. We can relate this y to the same given side and given angle to find the value of y. So looking even closely, we can say that sine now this time, because sine of theta is equal to the opposite over the hypotenuse. And we can see that by that being the opposite and then this being the hypotenuse in this case now. So it's flipped. So subbing those values in, we have that the opposite is y, and our hypotenuse is 8, and that's obviously, it's the sine of 45. And we have that y equals 8 sine 45. And what you may not know, but sine 45 is actually an exact value of sine root 2 on 2. So this is actually equal to 4 root 2 centimeters. And similarly with this is actually equal to 8 on 1 on root 2, which is actually equal to, let's just write 8 root 2. Cool. So now when we sub in all these values in terms of our, the area, let's find the area, considering that we have the height and the base length of this triangle. We have half times 8 root 2 times 4 root 2. And we can relate that to our 96 that we calculated earlier of the area of the entire surface, or I guess the front surface portion, so the front view, which is 96. And we come to see that that's obviously 16 times of 2 on 96, which is 1 on 3. Cool. So that is now telling us that the portion of this rectangle that's shaded in, this triangle that's shaded in relation to the rectangle is 1/3. So this is 1/3 of the entire surface in terms of its coverage. So now we can relate this area to volume. So what I mean by that is we can evaluate the volume of this normal cylinder and divide it by 3, and then we get the volume of the water section in terms of this manipulated, rotated cylinder. So you may know that the volume of cylinder is actually equal to the pi r squared times the height. We're referring to height as the perpendicular height again. So subbing these values in, pi times r, so we're given that this is 8, the diameter is 8, so the radius in this case is 4. So we sub in 4, and we square it, times the height, which is 12. And that's 16 times 12, which should be, let me just check real quick. It's 192 pi units. Cool, so this is now in centimeters cubed. Our volume unit is always cubed. And Now, so this is actually the volume of the total cylinder. So I'll label that total. So we want to calculate the volume of the water section as we rotated the cylinder. So how we get that value? So let's write volume of R, which is the rotated, I guess referring to this diagram now, of the rotated figure, is actually equal to 192 pi on 3, which simply is 64 pi centimeters cubed. So now we've essentially related the surface area of the water in the original. So what we've done is essentially related the volume of area it's filled in this diagram to some amount of volume, which we know now is actually a third of the cylinder is filled normally. So we can do that same ratio division in terms of its volume and obviously attain 64 centimeters cubed, which is B.